Hello and welcome to Ask Echometer. My name is Carrie Ann Taylor, and along with myself from Echometer today, we have Gustavo Fernandez presiding over the chat in our Q&A session. Also Ken Skinner, Tony Podio, Dieter Becker, and Lynn Rowland, who will be presenting today. So we have an Ask Echometer webpage that is accessible from our echometer.com website. And you can go there right now if you'd like and download the Session 21 PDF documentation bundle, where you'll find a PDF of today's presentation as well as 4 additional technical papers that Lynn's going to reference in today's session. Right next to that PDF bundle link is a link to download the TAM examples that Lynn's going to use today. So if you don't already have the TAM 1.7 software installed on your computer, you can download it from this software page, or there's a link directly from the home page to that TAM 1.7 install. All right, well, today's session is titled Over Travel Occurs on Up and Downstroke, Benefits of High Speed and High Resolution Data Acquisition. So Lynn, I'll go ahead and turn it over to you now.
Thank you, Carrie Ann. This presentation has been developed over several years, and the first time we really talked about this was back in a presentation was back in 2008 when we were talking about over travel, under travel, and then we recently wrote a paper, which is in 2017, talking about over travel, under travel also. And then this paper here doesn't really talk about, it talks about a little bit about over travel, but it talks more about the idea that the peak load and the minimum load, the load range, the farther apart the load range is on a surface dynamometer card, you typically can have a higher failure rate. And so that's based on some data, 6,000 wells in this paper right here. So there's several different things we'll talk about during the presentation. The idea of the high-speed sampling is sometimes when you over travel, the spacing of the plunger inside the pump changes, and you get a tag, and so the tag is sudden, quick, and in some cases you don't see it unless you sample fast. So we'll talk about high-speed sampling to be able to see a thing we call the pump-off tag. And so the idea of the speed, as a pumping speed, the strokes per minute increases, then the acceleration is a function of the speed. And the more acceleration you have, the higher peak load you have, and the higher minimum load. Now, the acceleration force on the upstroke typically is required to pick up the fluid load at the surface, and so at the surface there's a much higher force applied at the surface to apply the fluid load force at the pump, and that creates this a peak load. And then when we release the pump load on the downstroke, that also is an acceleration force that we create on the downstroke that creates the minimum load. And as we pump faster, we get the effect of increasing downhole stroke, which we call over travel, increasing the downhole stroke from going 0 strokes per minute. As the speed increases, the downhole stroke increases. We call that increase in speed due to the acceleration over travel, and then the under travel is due to picking up the fluid load. And we'll talk about that quite a bit during this presentation. And so we'll be looking at surface cards and pump cards and using those to be examples of how the well's performing and how the downhole stroke changes with respect to the surface stroke. So when we talk about producing sucral lifted wells, it's important to have recommended practices that improve the operation of the well. And some of those recommended practices are just installing the equipment properly, preventing corrosion, preventing rod on tubing wear with there's all different kinds of ways to do that. Identifying why something broke or failed, and then periodically surveying the well. And then we talked a lot about maintaining a full pump, and we'll talk about that also during the class. And we use a fluid level and a dynamometer survey to understand that the well is operating properly, and if there's any problems, we hopefully will see those and identify those and prevent them from becoming a problem in operating the well. We talked about Q-Rod recently, one of the Ask Echometer presentations, and that allows you to overlay your measured data with your predicted data, and they should match up. So when we have rod parts in a well, they're often caused by wear, and it's due to rod on tubing contact. It's due to incomplete pump fillage causing rod on tubing wear due to compression, and then impact loads. We'll talk about impact loads, and those can happen either upstroke or downstroke. Now, this is a peak polish rod load, and this is our normal dynamometer example well, and we've had that as one of the examples in our download file, and I'm showing you the peak polish rod load. And as the speed increases, the acceleration increases, and that causes this peak polish rod to increase. And so the minimum load, and basically this peak load here, I just popped up another note here, is that the peak load is created at the surface over the weight of rods and fluid by picking up the fluid load and applying acceleration force to pick up the fluid load. And this force is going to be higher than the fluid load that we're picking up due to the acceleration. Now the minimum load is the lowest load during the stroke, and typically it's going to occur right after the fluid load is released from the rods onto the tubing. And this acceleration force here reduces the rod, what you measure at the surface. You know, you're holding on to the weight of rods and fluid, but actually you measure here much less than the weight of rods and fluid due to the acceleration force created by releasing the pump load. Now, so I've labeled this force 1 as a force required to pick up the pump load on the upstroke, and the acceleration force 2, which is created by releasing the pump load on the downstroke. And this load range is the difference. And the paper that we just referenced back on the title slide has this in the paper that says this ratio between peak polish rod load and minimum polish rod load should be greater than 0.1 per each 2,500 foot. So if your well is like 5,000 feet, this ratio should be greater than 0.2. And here's this well. This well is 4,836 feet. And if you take the minimum polish rod load and you divide it by the peak polish rod load, that's a ratio of 0.25. And so in this case, we probably wouldn't slow the well down because of expecting higher failures. But if this minimum load was much less and this ratio became less than 0.19, we'd probably say, well, we're going to experience a higher failure rate in this well, and we'd probably recommend this to reduce the pumping speed. And so this is a good this number here of 0.1 per 2,500 foot of depth is a good rule of thumb, and it's something that I've practiced since the 1980s, and something that we should be aware of. So this is an example of an under travel card, and what under travel means that the surface stroke is much longer than the pump stroke. And in this case, our pump stroke is only about 18 inches long. And so the slope of the surface card is the slope of the stretch of the rod string. So the rods are stretching, and also the tubing is moving. The tubing is unanchored. And so we have 30.7 inches of rod stretch picking up the fluid load, and 8.3 inches of tubing movement from the fluid load being applied to the rod string, or being transferred back and forth, and tubing is moving. And then since we're not pumping at 0 strokes per minute, we're getting an additional downhole stroke of increase of 12 inches, and I call that over travel. And so you take this distance here, the total surface stroke minus 39 inches of stretch plus the over travel equals the 18.6 inch downhole stroke. And why do we get under travel cards? Well, we have big plunger sizes, or we can have a small rod string, or we can have extra mechanical friction like sand or scale or paraffin, or even in some cases maybe a dog leg severity, or even possibly over tight stuffing box. Now, when you see over travel, to me, when you look at the surface card, it looks like the surface card is pushing downward and to the right, and it's going to make the pump card have a longer down stroke. And so that's kind of an effect of it. When you go fast with the high, this wheel has almost 14 strokes a minute, then you get a lot of downhole additional stroke due to the acceleration due to the pumping speed. And so here we have a static stretch of 23 inches lost surface stroke due to picking up the fluid load, and then we get back 31 inches of over travel due to the high pumping speed, and that results in the downhole stroke being longer than the surface stroke. The surface stroke is 72 inches, and the downhole stroke is about 8 inches longer, 7.8 inches longer. So over travel cars, typically the pump stroke is longer than the surface stroke. In this case, we say what causes over travel? Well, maybe the rods would be parted. Tubing trolling valve could be stuck open. You could have a hole in the pump barrel and release the fluid load in the upstroke. The well could be flowing, and since there's no fluid load, you're going to have like no rod stretch, and so you get additional downstroke. You could have an unseated pump. Gas lock could cause that. A worn pump, which means very little stretch. A fiberless rod string, which has a lot of elasticity, or just pump. In this case, this well is pumping very fast, and that's causing the over travel pump stroke. And this is the example. So each time I pretty much each slide I show, I'll put the example file on the slide. Now, why is over travel and under travel important? Because what we found in the past is that if you have way too much over travel or way too much under travel, then you tend to have high failure rates. And this is a family of cards, surface dynamometer cards, that comes out of API RP 11, and it just shows that how as you pump with more fluid load, the card starts to slope up to the right, and as you pump faster, the dynamometer surface card starts to point down and to the right. So this is down and to the right is over travel, up and to the right is under travel, which means most of your stroke is being lost to stretch here. You're getting a lot of extra downhole stroke due to going too fast. So I'm going to show that with a Q-rod example. And so this Q-rod example, the well is going to be 5,000 foot deep with 100-inch surface stroke, 50 pounds of pressure at the surface, and the pump intake pressure, a 2-inch pump. The fluid load is 6,800 pounds. The tubing fluid gradient is that of fresh water, 0.433 psi per foot. The rod string that the Q-rod would design would be called a 7/8 rod on top, 6/8 or 3/4 rod on bottom, which is a 7/6 API rod taper. 41% would be 7/8, and 58.8% would be 3/4. The rod string in fluid in this well fluid weighs about 8,300 pounds. And the spring constant, the rod string is a giant spring, and if you were to stretch on the rod, if you were to pull on the rods at the surface or the pump with a 250-pound, 54-pound load, then the entire rod string would stretch 1 inch. Well, we're pulling the rod string 100 inches, and so if the pump didn't move, then 100 inches times the spring constant would mean that we'd have to pull on the rod string at the pump with a 25,400-pound force, and then the surface stroke would move up 100 inches, but there'd be no downhole stroke. Well, we're not actually pulling on the rod string with 25,400-pound pump force. We're pulling on it with 6,802 pounds. So the ratio, what we pull on it with what we'd pull on with 100% loss of stroke, that ratio is called fluid load over stroke length times KR, F over SKR. That's about 27%. So about 27% of the surface stroke is being lost to stretch. So here is the surface card and pump card going at 0 strokes per minute. Now, you can't go at 0 strokes per minute, but if you could, this would be the surface card and pump card. So the slope here is the rod stretch, spring constant, and here we're carrying the weight of rods and fluid plus the fluid load. And then at the top of the stroke, we've got 100 inches on the upstroke. The rods unstretch and transfer the load back onto the tubing. Tubing's anchored, and so now the pump stroke is exactly 26.8% less than the surface stroke. And since we're going at 0 strokes per minute, we've lost 26.8 inches of surface stroke to stretch, and there's no over travel. And so you have a theoretical pump card, a rectangular pump card, of the height of the pump card, and the pump card is 100 inches minus the static stretch. Now, if we increase the speed, something happens. As we increase the speed, we start to see a peak load here and a minimum load there. Why? Because of the acceleration force created by pumping faster than 0 strokes per minute. So now we're pumping 5 strokes a minute, and we still have the same fluid load, and we still lose the same 26.8 inches due to the fluid load being picked up in the rod stretching. So the surface stroke is still 100 inches, and we still lose 26.8 inches due to static stretch. But since we are pumping faster than 0 strokes a minute, we're pumping 5 strokes a minute, we get back 1.7 inches of over travel. Now, that means that since we have a speed that's faster than 0 strokes a minute, we have an acceleration force. We call it the F1 force to pick up the fluid load on the upstroke. And the weight of rods and fluid plus this F1 force equals the peak load. And then you take the weight of rods and fluid minus the acceleration force releasing the fluid load, and that creates the minimum load on the downstroke, minimum polish rod load. And so as we pump faster, we're going to increase the peak load and reduce the minimum load. Another thing that we might notice here is that we have a peak load, and then we have an echo of the peak load, and another repeat echo of the peak load. And the time from this peak to that peak is the frequency of the round trip travel time in the rod string. And we see the same time from here to here. We'll talk about that in a minute. So as we pump faster, we get 11 strokes a minute. We have a higher peak polish rod load with more acceleration because we're pumping faster, and a lower minimum load. And at 11 strokes a minute, based on a modified Goodman, allowed stress limits, we've reached our maximum stress load of 100%. And we're getting the same static stretch. We still lose 26.8 inches of stroke, down stroke, due to the rod stretch. But since we're going faster, now 11 strokes a minute, we get 13.8 inches of over travel back. And so the pump card is increasing in downhole stroke as you pump faster. But the load range is also increasing. And if it gets to be too much, typically we'll have an increase in failures. Now, based on API RP11L back in the when was it? Let's see. This is published. I don't see a date here, but it was there you go, 1977. This is pretty old. Probably older than most of the people that are watching this birth date. Most people born after 1977. So what is this? This is a nomograph that we used to use a long time ago to design sucker rods. And we just use Q rod. And we have F over SKR, the ratio of the fluid load divided by static stretch, is about 0.27 right in here. And so we ran the Q rod software at 0 strokes a minute. It hit right there at 0.27. And this is the N over O prime right here, so that's 0. And then for 5 strokes a minute, we're right there. And then at 11 strokes a minute, we're right there. And what I wanted to show is that when you run Q-Rod, it matches what we used to use by hand of the change in the downhole stroke compared to the surface stroke, that's the ratio, is the pump stroke to the surface stroke, is the Q-rod would match and calculate the same thing that we would calculate as what we used a long time ago, based on this nomograph that we'd created a long time in the past. So what kind of problems do we have when we pump off? Well, we have rod buckling problems, we have rod wear problems, we have rod on tubing wear problems, we have vibration stresses, we have severe rod loading changes, and we have pumping unit vibration problems. So these kind of problems are associated when you pump off more than 2% of the time. If you have an incomplete pump failure, more than 2% of your time, you're going to start to have these kind of problems in your life of your wells. Now, back in the 1980s, I wrote a sucker rod design program for Amrod Hess, and a guy named Norm Hine wrote one for Conoco. And Norm Hine had some design limits for the rod string, and he used F over SKR and N over O prime as limits, and I used the same limits, but we had different limits, and we thought those limits were very important. We thought those limits contributed to the lowest failure rates in the industry. And so this was company 2, Norm's company, and this is company 1, Amrod Hess, my company. And these were the limits that we used. And you can see that I used less than 0.2 and F over SKR, no more stretch than that, and N over prime less than 0.2. And Norm used more than that for his design limits. So we had completely opposite limits. And so here is the Q-rod calculations at 5 strokes a minute and 11 strokes a minute. And this is what my program did. My program said if your dynamometer data, your surface card fit in this area with N over prime and F over SKR, it was a good design. If it's in this area here, it's fair. If it's in this area, it was fair to bad. And then if it was in here, the red line is still, it would allow it, but it would say it was a bad design. But if it's outside that, it would say, don't do it. No, don't do this design. So this is what my program calculated. If it's out here in this area, it said don't do it. Well, Norm's program said only design sucker rods in this green area right here, and they don't match. See, I was saying Norm is bad or don't do it. Norm was saying, no, these are good designs, and so we were designing almost exactly the opposite rod string designs. And so I was saying over here, and Norm's program was saying over here, and we both had. He said, I would never design a rod string down here. And I said, well, I never designed a rod string up here. And we both thought and the people that we worked with thought these design programs were the very best. Okay, now here's the bottom line. And the bottom line is, look, company J and company H were down here with a failure frequency of 0.4. Only 40% of our wells failed, compared to other companies that have more than one failure per well per year. This is from 1990 to 2000. So both companies that had those two different sucker rod design methods had the lowest failure rates. So how can that be? What that means is that the rod string design didn't really matter and didn't have an impact on the life of the rods. Why? Because the service factor is there's such a big safety factor in the design. That's why. All right. So what do we have in common that made us have a long life? We had a practice of operating with a pump filled with liquid. That was our number one practice. We had technicians that went from well to well to acquire data, analyze problems, and then follow up recommendations. We had a practice to optimize, analyze, and troubleshoot our wells, and we tracked cause and condition of the failed equipment, and we actively did failure meetings on a monthly or quarterly basis. And then we also did root failure cause analysis of the failures, and that's what we had in common, even though we thought the most important thing was our sucker rod design software, which had no impact at all. Steve Gall with Oxy in 2016 and 17 and 18 did a study on their wells, and they had like 6,000 wells in their database, and we wanted to see how big a deal it was of this practice right here of operating with a pump filled with liquid. And I said it was a big deal. I said, Steve, this is a big deal. He said, well, how do you know? I said, well, prove me I'm wrong. I said, go do a study on your database and figure it out. He said, we'll just do that. We'll show you that doesn't matter that much. I said, it matters a lot. And so this is what he found, and this is a plot I've shown before. But what this shows is it shows that as you have incomplete pump fillage, which means more than 2% of the time, then you follow this line as a function of the stroke length times strokes per minute. And so your life of your equipment is 1 year if you're pumping 150-inch stroke at 10 strokes a minute. But if your pump is full, you're going to be up here. But if your pump is not full, you're going to be on this red line. If your pump is not full more than 2% of the time. All right, so what's the point? What's my point? My point is this curve right here. When Norm was building his design system, and he was going fast and short, he was operating with a 14 strokes per minute, but only a 54-inch stroke. And that is on this curve right here. And when I was doing my long and slow, I was doing 144-inch stroke and only pumping 5 strokes a minute. And I was up in here. So we were both operating with a full pump, but we were operating at either end of the curve. And it was validating what Oxy found and Steve Galt found, that says don't have incomplete pump fillage more than 2% of the time when you're pumping the well. You'll have a higher failure rate, and you'll be on a different curve. This is the 10-year curve right here, and this is the 1.5-year curve, and it has to do with how fast you pump and how long is your stroke. All right, so when we argued for 40 years back and forth at these meetings, and one person would stand up and say, long and slow is the way to go, or someone else would say, oh no, short and fast is the most economic way to go. Guess what? We were both right and we were both wrong. Okay? It's more important to have a full pump. So this is, you need to match your pump displacement with your inflow. If your well capacity, your pump capacity exceeds inflow, you need to control it with a pump off controller, timer, variable speed drive, or maybe change the stroke length or the plunger size. If you have gas in the pump, don't have gas in the pump. Run a properly sized downward gas separator. Because gas has an impact on the net pump displacement. It has to do with compression. And we want to either not have gas interference and not have incomplete pump fillage to control our pump displacement. So the way to go is to complete pump filled with liquid. And that's the way to go. You'll have higher longer life. You'll have less problems. If you have incomplete pump fillage, you'll significantly impact the life of your equipment. And so you should be determined to maintain a full pump. Now, we just talked a minute about the frequency of the rod string. And so when you pump faster, you could pump at a ratio or a multiple of the frequency of the rod string. And so there's this equation that calculates the rod string frequency if it's a constant diameter rod. You take 15 times the acoustic velocity in steel divided by the rod string length. Let's say it's 5,000 foot deep. And if it's a taper, like a 7/6 taper, then there's an adjustment factor. This is like a 10% higher frequency if it's not a constant diameter. So this 5,000 foot long rod would have a frequency of 48.9 strokes a minute. And you don't want to pump at 48.9 strokes a minute, or your pump won't move and your rod string will go up and down. You have a standing wave in your well. But if it's tapered, you don't want to pump it 53.4. So what does that mean? What that means is that if you look at your surface dynamometer card and you see a peak load and another peak load on the upstroke, the, the, the distance from here to here is a certain amount of stroke, upstroke, then downstroke. And this, from that peak to that peak, is 57.9 inches. And this exact same well, and this is an example of dynamometer change strokes per minute, at the exact same well, a little faster at 5.22 strokes per minute, this distance is 71.1 inches. And then if you pump faster, this distance from this point to that point, you move a little faster, a little farther, but there's a peak load and an echo peak load. And what I'm going to say is that the time between this peak and that peak, or that peak and that peak, or that peak and that peak, is exactly the same no matter how fast you pump, how fast your pumping speed, because the time between that point and that point is based on the fundamental frequency of the rod string. And so it takes 1.31 seconds in this well for the force, the peak load or the minimum load, to travel up and down the rod string, up and down the rod string, and that's a repeat echo in the rods. Now, so what that means is if I take this is a load versus time, and I plot the load versus time on the upstroke, and I overlay it, the peaks match up. But if I look at it, the red curve is 4.85, and then the green curve is a little taller, it's 5.4, and the blue curve is 6.1. Look, even though they occur at the same time, as you go faster, you get higher and higher peak loads. Okay, how come we don't see the same number of, so the question often is there a problem with my rod string if I have 1, 2, 3, 4 peak loads on the upstroke? Does that cause more cyclic loading? And the answer is, well, no. It's the rod string has the same number of cycles per day based on the frequency of the rod string. So every 1.31 seconds, there's a frequency, an echo. Doesn't matter how fast you pump. So if I look at the downstroke, these lines don't line up. But if I start to line the minimum load up and just line them up, I shift them, then the minimum loads line up. And again, notice the blue curve has the fastest speed. It has the lowest minimum load. Okay, so that's the impact of increasing pumping speed. You have higher peak loads and lower minimum loads, and you get more over travel. All right, now this is a diagnostic pump card shape, and it's called a delayed closing of the trailing valve on the upstroke. And it's a sudden impact load. And if you were standing near this well and you felt it, you would feel a huge impact at the surface near the wellhead. So here's two different examples. This one is called gunk in the pump, and this one is called a trailing valve double valve pump. Sometimes people call this a two-stage compression pump. Now, so here the chemical in the pump kept the trailing valve from closing, and then it delayed closing and it closed suddenly, and the pump suddenly applied about a 4,000 something pound load to the bottom of the rod string, and since the polish rod is moving faster than 0 strokes per minute, that creates an acceleration of force to the surface that's about 6,000 pounds high. So the load at the pump is smaller, the acceleration force to the surface is bigger due to the pumping speed. And then this is an echo, an echo, an echo. Now, this is going to cause increased failure rates. Now this is a well that has a double valve in the pump, and on some strokes, you can look at the example. On some of the strokes, and we may have time to look at the example when we get through, this 6,500 pound impact load to pump is a 10,000 pound impact load to surface, and this was causing the rods to fail about every 6 months. And this was causing rods to fail about every 6 weeks. So it really increases the failure rate because the rods don't like to be in a huge impact load uh, hitting the rod string. And so here you can see this is a plot versus pump load and polish rod load versus time. And it takes time. It takes time for that force to move up the rod string. So the impact load occurs at this time, and in 6/10 of a second, it's felt to the surface because it took time for that force to move from the bottom of the well to the surface. And then it repeat echoes, echo, echo, and so on. Well, what happens if you look at the velocity? The green curve is the velocity of the polish rod, and the red curve is the velocity of the pump. And when that impact load occurs, the pump stops for about almost a second. This is almost a second in time. And the motor, when that impact load hits the surface, the motor stalls out, and you see about a 6 inch per second change in the polish rod velocity. We can use the analysis plots to overlay these plots and see it. And you can see here that I overlaid the polish rod load in green on top of the polish rod velocity in red. And there's that drop in load when that impact load hit the drop in velocity when the impact load hit the surface. This is an animation that shows the impact load occurring downhole. And that's a little bounce. If you see that little fuzzy part, it's a bounce. There's a bounce right there. And so there, bam, it hits, and you can see the impact at the surface. So increases your failure rate when that happens. Now this is the gunk in the pump, and I'm looking at the field view, and this is the stroke, the data set that I'm looking at, and it's in the field view. You can look at the different strokes and select them and overlay them, and you can see how the impact is occurring. Now this is kind of a tricky problem because this was due to batch chemical treating the well, and you dump chemical down the casing, and then nothing would happen as the chemical fell down the well for about an hour and a half, and then for another about 2.5 hours, then the gunk would start to go through the pump and would cause the trolling valve to not go on the seat, and then you'd see this impact load, and then after about 4 hours of time, the well would clean up, and it would be back to with the normal dynamometer card. So this was one that you had to catch to see this sudden impact problem. We were doing a best practices meeting every quarter with a group called Alioc and Midland, and this is a plot of the failure data for this field, where over a time period when they were using this batch treating method, the failure rate changed from 0.4 failure frequency to every well in that field had a failure every year. So that was a pretty bad deal to have done. Does the impact load impact the gearbox? And the answer is yes. When you look at this 456 gearbox right here, it's in that torque, and that echo, just the echo of the impact load right there on the upstroke, caused the gearbox to be overloaded by 40%, which would result in a gearbox life of maybe just 1 year. So it's a huge reduction in gearbox life also when you have these sudden impact loads, not only impacting the rod string, but impacting the rest of the artificial equipment on the well. So how do you see this? Sometimes you can't see this. And so this impact load, this time from here to here is a very short time. And when you sample the data on a analysis for dynamometer analysis, you might sample at 30 samples a second or 60 samples a second. Well, some of these impact loads are so sudden that you can't actually see them. They happen quicker than you can see them if you're sampling too slow. So one of the things that we say is if you see a sudden load change on your dynamometer card, we recommend you change the sampling speed to 240 samples a second for the dynamometer data, and maybe even 480 samples a second, and that will allow you to see the data. If you do, this is in TWM here. This is TWM's drop down. Just before you click the start button, you change the sampling speed over to the right. In TAM, you go to utilities and pick sample rate, and then you can tell either for wireless equipment or well analyzer what sampling rate to use. And the default would be 60 typically, and you're going to change it to 240 or to 480 if you have some kind of impact load occurring on your wells. Now, this may be confusing, probably is, but this is represents an impact load, and the time for it is short. And so this time from here to here, well, actually it's a wave, from here to here is only 1/10 of a second. So if you're sampling 20 times a second and you have a impact that creates a acceleration impact that's 1/10 of a second wide, you get 1, 2, 3 points, and that's all you see if you're sampling 20 samples a second, a straight line. But if you sample 240 samples a second, you get like 1, 2, 3, 4, 5, 6, 7, 8. You get like 16 you get 30 something points over the entire 1/10 of a second. So what's 24 points over the entire 1/10 of a second. So if you have a sudden event that takes a very short time to occur, you have to increase your sampling speed to sometimes to see it. Now, if you have a noisy sensor and sensor's not high resolution, and you increase the sampling speed, you just increase the noise. So it's important that you have not only high speed sample but low noise sensor. Now, this is this 240 sample data in TWM, and there's a bug in TWM, though we haven't fixed it. If you put some high speed data in TWM, the wave equation becomes unstable and it looks like this. But if I take the exact same data and put it inside of the TAM software, which you can just import it right into TAM, then this is a pump off tag. And so we wanted to see this pump off tag when the incomplete pump fillage caused the plunger to move down in a barrel and hit. And if we were sampling slow, it's hard to see. If we sampled fast, then we could see the actual tag. But in TWM we couldn't see it at all because the wave equation is not stable for that well depth and 240 samples a second. All right, so this is just saying what I already said. You need to have high resolution data if you sample at a high speed. The data needs to be not noisy, because if you sample at speed, you're going to amplify the noise. Now, this is examples of tagging with sampling speed. And so when we collected this data at the well, we sampled at 30, 60, 120, 240, 250. And this is what it looks like at sampling 30. The default method for TWM is 30. And the tag, I would say this is just an ugly pump card. And I said, I just don't like fiberglass rods because they always look like an ugly pump card. Well, that was not the right thing to say, but that's what I said. I didn't realize a long time ago that if I sampled faster, I'd actually see more descriptive information. So this is the same data as this. The only difference is same time. The only difference is this is sampled at 30 samples a second. This is sampled at 240 samples a second. And I can see the actual real character of the tag when I sample fast, but I can't see it. It's smoothed out over here. All right. Now, another thing you might notice is that if you have a fiberglass rod string, you often see a drop in load on the surface dynamometer card when there's a tag. So this is a indication of a downhole tag, even if you don't see it in your pump card. If you see this drop in load on the surface, that probably means you're tagging downhole. Now, this shows the idea. Look, here's the points from sampling at 30 samples a second, and see how it's kind of smooth this actual signal out. And so if you sample too slow, you smooth the signal out, you can't see it. And so we don't want to smooth it out. So here's the real tag, and there's the smoothed out tag because we sampled too slow. Now, why don't you sample fast all the time? Because the data files are huge and it makes the program run slow. So usually you sample 60 samples a second, and then if you see a sudden impact load, you're going to sample faster. So here, bam, there's a tag, and there's a repeat, 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 repeat. And so that's that force traveling up and down the rod string. Now, if you look right here, you see when the first tag occurred, it stopped. The pump stopped. That's the pump plunger velocity. And then the repeat, the plunger started moving. And then the repeat stopped it. And then the repeat, it's moving. And so on. So the force, this force in the rod string is a real force. It's moving up and down the rod string. And it's impacting the behavior of the pump as it echoes up and down the rod string. Now what's this? Here is the polish rod velocity in green. This is polish rod moving up. And then there's the top of the stroke. Here's the polish rod moving down. And then right here, the polish rod is moving down at about 15 inches per second. And here the plunger is moving up at about 15 inches per second on the downstroke. And this is a fiberglass rod string. Well, you don't want this. You don't want your fiberglass rod string in compression on the downstroke. And so if we look right here, that's that right there. So that right there is a polish rod moving down and the plunger moving back up. And that occurs when you have fiberglass rod string, your pump's not full, and you have gas compression, and then that's a bounce of the fibrous rod string. And when we say bounce, we mean that the polish rod plunger's moving down on the downstroke, and then it starts moving back up. And so it moves back up right there, which should increase rod failures. And this is an animation that's going to show the tag, and then you can see the velocities, and you can see the repeats versus time. And this is the tags versus stroke, and the repeats versus stroke. And you can see here that these aren't equally spaced in time because it's plotted versus plunger stroke. But here they're equally spaced versus time because it's plotted versus elapsed time for the stroke. So sometimes we look at a plot, it makes it more confusing because look how there's more distance here, but it's the same time between those echoes. Now, back in about 1984, when I was working on the wave equation for Amarada Hess, I walked into my boss's office and said, Paul, I said, when I look at the bottom of the stroke for the surface card, and I look at the bottom of the stroke for the pump card, sometimes they don't line up. And I said, I think they should line up. What do you think? He said, yeah, I think they should line up. I don't think we knew what they should do. So from then on, I would look for the minimum point on the pump card, and I'd subtract it from all the points of the position on the pump card. And I made the surface card and pump card always line up. And that was the convention that we had. But actually, based on the velocity of the rods and the change in load, and based on the speed, the position of the plunger inside the barrel moves and changes as the acceleration forces change in the rod string. So when we look at this well right here, that has the 6,500 pound tag, the bottom of the pump stroke relative to the bottom of the zero is 22.4 inches to that way, to the left. So normally I plot it like this. Let's see if I can. Right here, I plot them at the same zero. So the pump zero, the surface dyno card zero are all in the same zero position. But we've added to TAM an I&I option that allows you to turn an option on that you can let the pump card float based on the wave equation and not make them match. And we play with it a little bit, but it's basically turned off and you have to turn it back on if you want to try it out. So it's before I said this, and it says, now, when the pump's not full, that changes the velocity of the rods on the downstroke. What do I mean by that? The velocity, this is plunger velocity. The velocity of the rods tends to be faster, higher velocity, when it's compressing gas. Okay, and going and the trailing valve is still closed. So right from here to here, the trolley valve's closed, and there's more load on the rods from the pump, and so the pump tends to go faster right here, and that tends to change the position of the plunger inside the barrel. So when does a pump not be full? Well, when on a pump off controller, when it pumps off. And so I was teaching a class about 5 years ago, and someone in the audience said, "What about pump off strokes?" And I said, "I don't know what a pump off stroke is." And he said, "Well," he said, "every time our wells go down and pump off, we get a tag." And I said, "Cool." I said, "I've never seen that, but it makes sense." I said, "It makes sense because since the load on the downstroke is being maintained, it's going to cause the plunger to move deeper, and that's going to cause a tag." So this is a well that Ken and I went to, I don't know, quite a while ago, and it had a variable speed drive on it for pump off control. Instead of pumping off, it slowed down. And you can see that the width of this line here is a function of the pumping speed. As you go fast, this distance is close, and if you go slow, this distance is farther apart. And so we're going fast and then slow and then fast and then slow and then fast as the speed of the variable speed drive changes to try to maintain a pump filled with liquid. And this is a rod string, had some fiberglass rods in it, quite a bit of fiberglass rods. It was about almost 10,000 foot deep. And so here is the animation of this data, and it starts off going fast, 9 strokes a minute, and the pump is filled with liquid, and then it starts to pump off, and the variable speed drive is going to start to try to slow the system down. And so as the variable speed drive or the pump off controller starts to register incomplete pump fillage, you're seeing the speed drop. Okay, and so the speed's going to drop and drop and drop as the strokes continue to stroke. I'm going to speed up just a little bit here. And now we're going the slowest speed, about 4.7 strokes a minute, and we're pumped off. Okay, but now we're going slow, and the gas separator starts to have separation starts to occur. Because why did it have incomplete pump fillage? Because we were going too fast and we're exceeding the capacitor separator. And so now, as we're going slow, the separator is starting to work again. The gas is starting to escape out of the separator, and the separator is starting to fill back up with liquid. And if we'll go over here a little farther, we'll see that we're still going slow. We're still going slow. We're still pumped off. And then let's go a little farther here. We're still going slow. We're starting to speed up a little bit. So the pump off controller is starting to say, hey, I think the pump's filling up. Now it's filling up, and it's starting to go faster. And so if you look at this data, what your observation would be is that if you go fast, the pump's full. If you go slow, the pump's empty or pumped off. And it doesn't. The real thing is, if you go fast, you exceed the capacitor separator because the gas separator fell, and then your pump has to slow down. Pumping system has to slow down to let the gas separator regain its separation capacity. Again, look, here is the position of the pump when the pump relative to the surface card. It's 8.4 strokes per minute, and it's going slow, about 4 or 5 strokes a minute. And when it's seeing a change here, it's trying to slow down, it changes in the middle of the stroke. That's going to create some acceleration forces in the middle of the stroke. So that was a problem. But now notice here we went from about 5.6 strokes a minute to about 9.2 strokes a minute. And now notice the bottom of the stroke has moved relative to the surface card about 26 inches deeper. Well, not deeper. This is 26.9. That's 8.4. So that difference is about 18.5. So this stroke here is about 15, the plunger is about 15 inches deeper in the barrel, 16 inches deeper in the barrel. And so that's due to the faster pumping speed. It's moving the plunger in the barrel deeper as it pumps faster. So we're comparing this at 5.6, and the bottom of the stroke compared to the surface zero is 8.4. We're comparing it here, it's deeper, and so the plunger is actually moved in the barrel. Why am I showing you this? Because this is how the pump off stroke occurs. The pump off stroke occurs when the plunger moves deeper in the barrel because of the acceleration force created by the force on the downstroke being maintained on the rod string. All right, so here's our pump off tag. So we see that this pump card relative to the surface stroke is about 5.5 inches lower than the zero for the surface card. And we can see here that on the downstroke that this load's almost the same load, and it's compressing the gas and the load's been transferred. And if we look, we can see here that during this transfer right here, that the plunger velocity is high on the downstroke, and then it quickly slows down right there to open the trailing valve, and then it speeds back up, and then it tags. If we look at the full card, which is this blue stroke, we compare the blue stroke to the pump off stroke, we can see that the blue card is close to zero, and the pump off tag is about 5 inches deeper in the stroke. So just a little bit, if you're spaced out close, just a little bit more downward over travel, and you're going to cause a tag. Notice that the incomplete pump stroke has an overall stroke length of 151 inches, and the full stroke has only 131 inches, so there's actually 20 inches of over travel when the well's pumped off. With the pump off stroke, we get this much over travel and this much additional over travel on the downstroke. We get both over travel on the upstroke and the downstroke. Now, this is another example here of over travel on the upstroke. And so the surface card here shows a sudden release and the fluid load on the upstroke. And the sudden release in the load is due to a hole in the pump barrel. And so the rods were stretched out in the upstroke here in this fluid load. And then in an instant, this load is released. And we can, if we sample fast, we even see how long an instant is. It's probably less than about a 30th of a second. Maybe not quite that, pretty quick. And that causes a sudden release in load, and the rods unstretch on the upstroke, and that creates this additional over travel. And so the pump stroke has longer stroke than the surface stroke due to the release of this fluid load on the upstroke. Okay, this is a rod part, and we show that the pump stroke has 169.3 inches of downhole stroke, and the surface stroke is 168. So on a rod part, deep rod part, there's about 1.3 inches of over travel because why? There's no stretch, so there's no stretch, loss of pump stroke due to stretch, and the total downhole stroke is longer due to the acceleration or the pumping speed of pumping the well. So one time someone said, is over travel good or bad? It just happens. I mean, as you pump faster, you get more downhole stroke. So in that condition, and we want over travel when we run fiberglass rods, so over travel would be good because it increases our downhole stroke as we increase with the SPM. But if you go too fast, what do I mean by too fast? If the ratio of the peak polished rod load divided by the minimum polished rod load divided by the peak polished rod load is less than 0.1 per 2,500 foot of depth, then you're going to have an increase in your failure rates. That's what we've seen with experience, and now that huge database that discussed in the paper that we attached. So, is long and slow good, or is short and fast good? Well, as long as you have a pump that's filled with liquid and you stay within some limits, then they're okay. There's no difference between long and slow or short and fast. And typically we're talking about operating in a range between 5 and 10 strokes a minute. So what I hope you've seen in this presentation is that as we change the pumping speed, we create forces that cause the pump to over travel, and we have under travel when we pick up the fluid load or rod stretch. The sudden release of the loads on the upstroke cause over travel on the upstroke, and if you have a sudden release of load on the downstroke, that's usually called a pump off, that's going to cause an increase in failure rate if you do it too much, more than 2% of the time. The idea that the surface card and pump card plot with the same zero position is convention, because they don't. Most people that display a surface card and pump card plot them with the same zero position, but it's a relative position, and for me, I've been plotting them the same since about 1984. When the pump is not filled with liquid, that changes the forces acting on the rods in the downstroke, and that tends to cause over travel in the downstroke, and it can cause the pump off tag that we talked about. So the release of the fluid load premature on the upstroke or not releasing on the downstroke, have incomplete pump fillage, tends to cause increased failure rates.
We have a couple of questions.
Okay, good.
Here, let me start with the last one. So that's slide number 56 on the left-hand side where you have the hole in the barrel. They're asking if a pump is top anchored, can we see the hole in the barrel? We use top anchored pump in shallow wells.
Well, it's just like a hole in the tubing. So if you have a top hole down pump and the pump sticks out the bottom of the tubing, and you get a hole in the barrel, then that's like a hole in the bottom joint of your tubing string, and the liquid just leaks out, and so you'll have a hole in your tubing. It'll act like that. It'll be a leak. No, the answer is not really. You can't really see this kind of display, because the way this works is that when there's a hole in a pump barrel on a bottom hole down pump, when it leaks, the pressure equalizes, and so we're pulling the standing valve ball off the seat here, and the plunger's moving up, and it's maintaining low pressure inside the pump chamber, and then right here when the pump bottom of the plunger goes by the hole, then the pressure equalizes, because on the outside of the pump barrel is the tubing, in between the tubing and the barrel is the tubing discharge pressure at the top of the pump, and it equalizes the pressure on top of the pump to the pressure equal on the bottom of the plunger, and the fluid load is gone because the pressure equalizes. So this is created by the bottom of the pump moving past the bottom of the plunger, moving past the hole in the pump barrel. And so if you have a hole in the pump barrel for top hole down pump, just like a hole in the tubing, liquid leaks out. Here the liquid doesn't leak out. It's held in the tubing because the pump is seated in the seating in the cups, and there's no leak. It doesn't leak out. It just leaks out of the barrel. The pressure equalizes. It doesn't leak out of the tubing. So the equalizing pressure causes the fluid load to drop off. That's the answer.
Okay. Now slide number 36, where you had the gearbox torque plot.
Yep.
There. The question is how a pump in tagging impacts a gearbox loading and run life. Is it tagging an impact force applying on the gearbox when it's tagging down? Then has another question if there is any paper describing this condition. So what's the impact of that on the gearbox?
Right. So when we talked about torque on the gearbox, we did an Ask Echometer presentation about net torque on the gearbox. This is the net torque on the gearbox. And so when you calculate the net torque, you take the rod torque minus the counterbalance torque. And so this is the rod loading, and you take the rod loading minus structural imbalance times the torque factor. And so right there is the rod loading at the polish rod minus structural imbalance times the torque factor is that torque value right there. And so there's a lot of extra rod load here compared to the counterbalance moment, and that causes a high net torque, rod torque minus counterbalance torque. And so this is a force acting at the polish rod. All of this is force at the polish rod, and then this is the calculated net torque of the gearbox. And so there's the impact load, and then there's a repeat and a repeat and a repeat. As we talked about going up and down the rod string at the frequency of the rod string. These are bam, 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 bam. And that peak load, even though it's less than the peak load, see the peak load right there is 16,000 pounds. Well, the peak load there is 18,000. The rod loading is even less right there, right here is 2,000 pounds less. But even though the rod loading is 2,000 pounds less, the rod loading minus structural imbalance times the torque factor is that rod torque is much, much more than the counterbalance torque and causes this huge gearbox net torque load, and it's damaging the gearbox. So it's the net torque on the gearbox, rod torque minus counterbalance moment, that is what's causing the overload. Okay? It's not the tag on the gearbox, it's the huge rod load at the polish rod causing a huge net gearbox torque at the gearbox. Okay.
Yes, at that point the crank are more to the horizontal than to the vertical, and the torque factor is much higher at that point.
Yeah, we can look at this. I don't know if I have this data. Do I have this data here? This well is the gunk in the pump. We can look at this well because we have that example. So we'll look at this well and look at the torque and revisit this question when we look at the data.
Okay. And one more question is related to slides number 9 or 10, where you have some dynamometer cards from Q-Rod. And based on the definition, there is a slight confusion there, because based on definition, under travel is when we have a higher stroke length on surface compared to the pump stroke.
Under travel.
That's under travel.
Right.
But also, every time that they run a design on Q-Rod, it shows over travel value on the lower right-hand side.
Right. So the static stretch. So the surface stroke minus static stretch plus over travel equals the downhole stroke. Okay, so let's go right here. So 100 inches minus 26.8 plus 1.7 equals the pump stroke of 75 inches. So an over travel pump card has a longer downhole stroke than the surface dynamometer card. An under travel pump card or surface card has a shorter stroke, well, usually a much shorter stroke than the surface stroke, and the surface card for over travel points down and to the right, and an under travel surface stroke points up and to the right. So the term, that's a definition term issue. The term over travel means that the pump stroke elongated, okay, due to acceleration. In this definition here, we're using it just to represent increasing inches of downhole stroke due to acceleration. So here they would travel 0, here it's 1.7, and here it's 13.8. That's at 11 strokes a minute. So on this screen, we're calling over travel the increase in the downhole stroke over the loss due to the static stretch. Okay.
Correct.
It's not the same. It's not an over travel card or under travel card. It's actual the under travel and the over travel. Okay, static stretch is under travel, and acceleration lengthening. We don't have that term here. We just call it over travel.
Wait, I hope that clarifies any doubt that could be there.
Yeah.
Okay.
If it didn't, send us an email. We'll try again. So, but
No,
it's just a word that we use. Over
yeah,
travel represents increase in
yes,
downhole stroke
yeah.
due to acceleration.
That doesn't mean that the comparison of the pump cards and the surface card shows over travel.
And in this case, this is an over travel dynamometer card. Okay. In this case, it's not an over travel card, even though there's 1.7 inches over travel. Right? Say yes.
No.
It's not an over travel card.
Not over travel.
Yeah, but there is over travel in the calculations. All right. So is there any other questions? Is that it for now?
Just an extra comment that I'm getting for that condition where we have a hole in the barrel on the upper hold down pump, and if that's the case, acting as a hole in tubing, fluid level inside the annulus and the tubing would be about the same depth.
Yeah. In fact, there hopefully we'll do a presentation, another Ask Echometer presentation, sometime in December, I think, on finding holes in tubing. We'll talk about that. Usually the fluid levels and the tubing and casing annulus are within about 1,000 feet of the same. So that's what we've seen in out in West Texas and many wells when you have the hole below the liquid level, that the liquid level in the casing and tubing aren't exactly the same because there's different liquid in the tubing and casing, and the only place the pressure is equal is at the hole. Okay, yeah, at the hole. Is that right? At the intake.
Yes.
Anyway, it's the liquid levels won't be the same height. They won't be the same place on tubing and casing. But we'll talk about that.
And that's for pumping wells. And gas lift would be completely different because we have a packer.
That's right. It's even more restricted because of packer in the casing.
There is good data to show about that. Well, that's all the questions I have so far, Lynn. I think you can jump into the examples. We have plenty of examples to show.
Okay, so if you go to our webpage and you go to session 21, there's some examples. And if I go, this is the first example I showed, and I was really just saying that we use the surface card and pump card to analyze a well, and that's the only reason I really put that slide on here. But I went ahead and put this example in the data set. But the example I want to talk about first, it'll create this folder on your computer if you install on your computer under a folder called Echometer Online. There'll be an over travel folder, and I think I put together about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 examples. And so the first one I go to is the one that we were talking about a minute ago about gunk in the pump. And so if I go to the one with the gunk in the pump and open this one up, and this is a series of tests. And if you look, here's a test at 514. And if we go back and look at the dynamometer history, there's quite a few examples. And the first example in the morning didn't show any problem at all. And then at 5 in the afternoon, it didn't show any problems. But in between those two, they dumped chemical down the casing right here. And that caused these pump cars to start having problems where the trailing valve would delay going on seat. And so the one that I want to grab is the one, I think this one right here. This is the one that had that big peak load right there.
Yes.
So I'm going to go click on this one, and I'm going to go to the field view. Okay, and there are all the strokes overlaid. And if I bring up the advanced viewer, I can take my mouse and run across these strokes until I find the stroke that is that one right there. So that one right there, stroke number 3 is the one I want to look at. Everybody see how I did that? I went to the field view and I click on one of these, only one shows up. But if I hold down my shift key and highlight all these strokes, then all of them are overlaid, and I can go through and find the particular stroke I want to look at without having to go through stroke by stroke. If I click on stroke number 3, that's the stroke I want to analyze, because I want to see that spike right there. How does it impact the net torque on the gearbox? And so if I close this out, okay, now I have this stroke selected. If I go to Details View, I have this stroke selected. If I go to the analysis plots, I think I've got torque. Let me go look and see real quick. If I click on Edit, and I click on Lift System, I've got a Mark pumping unit with a 456 gearbox, and I've got counterweights on the crank. I've got OAR master weights and OAS auxiliary weights, and so we've got the information for torque. So this is going to tell us our counterbalance moment. We've got 1,200 K inch-pounds of counterbalance moment based on the cranks and the weights on the cranks. All right, now if I close this out, I want to say save, but there's nothing to save. If I go look at the report and I look at this data for torque, I'm gonna make it bigger and make it fill the screen up more. Okay, so now that's, and it says right here that we're overloaded on this guy, not 138, but it says 136. So let's scroll down here and look at this, and we can see right here that this is called the permissible load diagram, and this peak load right here is what's causing the gearbox to be overloaded, and that peak load wasn't causing the gearbox to be overloaded. It's for Mark pumping units. The permissible load diagram typically slopes down and to the right, and it works the best for over travel cards for Mark units. And so when you have a high load right here, in this case due to the echo of this trailing valve closing on the upstroke, causes this huge acceleration impact load, then that repeat, 1, 2, 3, 4, the fourth repeat of that impact load causes the rod loading to exceed even the you can't even balance it with the weights on the cranks that currently are there. You can't balance this pumping unit. It's overloaded. It's exceeded. So if we go down to the very bottom here and we look, it says that we have a peak gearbox load of 624,000 inch-pounds. Okay, and that's probably coming from that spike right there. That's where it's coming from. So that spike, that's the existing net torque. So that spike right there is which causes this overload of the gearbox. Now, if we go look at the analysis plots, and I'll try to make this make sense. This is, if you look at the analysis plots, and we're going to plot this. Let's just plot it versus elapsed time here, and let's plot seconds instead of clock time, because this is the clock time here. I want to plot in terms of seconds. All right, so here is the polished rod load, and I'm going to come down here and plot the rod torque. Okay, and if let's do it up here, rod torque, there. Okay, and so doesn't show up quite as good here, but that's the rod torque. See how the rod torque isn't higher rod torque here, but this rod torque is less than that rod torque there. So the inch-pounds, 1,000 inch-pounds. Okay, the difference between the rod torque and the counterbalance torque is the net torque. So if I plot over here the counterbalance torque, okay, that peak and the counterbalance torque line up, and that peak is far away, much farther away from
Combine the axis.
And so if we were to make the net down here, let's make net over here, net torque existing, then when we look at this, we see that the net torque here, oh, combine axis, thank you, there you go. Now it's the same scale. So good call, Gustavo. So this one is much more distance between the rod torque minus the counterbalance torque, which means there's much more net torque on the pump unit due to that peak load at the polish rod. Now, I don't know how to explain that any better, but that's what that's from. You can see that this is the torque at the gearbox calculated with this is the counterbalance moment, and this line represents the rod loading times the torque factor, rod loading minus structural imbalance times the torque factor of that load, and that distance, this distance here, is the net torque on the gearbox. Even though this load here, that's this green line right here, or the red line was measured at the polish rod. So someone said, is the impact load impacting the gearbox? Well, it's impacting the rod, but it creates a torque, net torque on the gearbox. Is everybody so this load is at the polish rod, but this green line is the net torque at the gearbox. So that's what's causing the net torque at the gearbox is what causing the damage. And the interesting part here, I would say, is that the peak rod load has less torque than the Echo because there's less counterbalance torque for that crank angle. All right, hope that cleared up that question. But you can use TAM to see this. It's kind of cool. You can go through and look at the data and go see, here's the gearbox torque, rod torque, here's the counterbalance torque, here's the difference. Yeah, that's what's causing the huge torque. All right, let's go look at a different well. This well we've looked at before, but I like this example because what it shows, there's three examples here. There's let's look at dynamometer data. Okay, so this one is going like less than 5 strokes a minute, and you see 1, 2, 3, 4 echoes, and so this force here on the rod string is a force. That's a double word, and since it's at the surface, it just doesn't disappear. It travels back down the rod string. It goes all the way down to the pump, and it comes back up, and it takes from this point to that point that much time to travel round trip. And that force doesn't just disappear. It travels back down the rod string and back up, and it travels back down. Here it is again, and back at the surface. And the time from here to here, and here to here, and here to here is exactly the same. So if we go look at the analysis plots on this well, and we plot this versus elapsed time, what we see is that if we take this line here and move it to that point, and then we move it to the next one, we'll see that between those two lines it's 1.31 seconds. And between that one and that one it's about 1.31, and between that one, you can't tell exactly where that occurs, but it's about 1.31 seconds between each of those echoes, and the same thing on the downstroke. The minimum load and then the repeat echoes. Now, when you go faster, the next stroke here, when you go faster, you're going, that's not faster. You go faster, here's 5.4 strokes a minute, and we go to the analysis plot, and we look at we can look at load versus time if you want. Polish rod load versus time. And you again see that this echo, 1, 2, 3, 4, the time between those peaks are pretty close exactly, to 1.31 seconds apart. And the same thing on the downstroke. Now, I think if we were to go to the very last one here, and again plot peak load, let's see if we can't do this, peak polish rod load versus elapsed time, okay, and this one is at a speed of 6.08 strokes per minute. So now we've got three different strokes, 4.86, 5.4, and 6.1. And if you look at the analysis plots on all three of these, let's look at all three of them. Look at the analysis plots and make them all the same. Rod loading. Let's see if I can get this to work. Sometimes it doesn't work. If we overlay them, we'll see how they compare. And so let's go into oh, I can't click the button. Let's go here. And we'll go to field view, and I want to overlay all three of those strokes. So I'm going to click on annotations and go to previous strokes, and I'm going to select each of those strokes. So this was 11:02:01, that one, and that one. Okay, so now I've got all three strokes that are overlaying each other, and you can't see anything here hardly, because the speed is changing where these peak loads occur, and it doesn't look like they match up at all. And so all we're seeing is that as we pump faster, you have higher and higher peak loads. But if you go to the analysis plots, it doesn't show them. I was wanting to show all three of the. Yeah, it didn't show all three plots on the analysis plots. That's what I was trying to get to, but it didn't work. I don't know what I did wrong to make them. But anyway, I have them in the graph where we showed that, and these peaks all line up because the time from here to here and here to here to the peak load is the same for all three dynamometer cards, even though the speed is changing from 4.86 strokes per minute to 6.1 strokes a minute. And you can see that the downhole stroke is slightly changing due to over travel. As you pump faster, the longest downhole stroke is the 6.1 strokes a minute, and that's because we've added more acceleration, more speed, and it has the longest downhole stroke. So that's what this example. This is a good example to compare and see how slight speed changes can affect the surface dynamometer card. And the reason why I like to talk about this a little bit is because I bet I've had, I don't know, probably 100 questions about how is 4 peak loads on the upstroke, is it worse than having 3 peak loads on the upstroke? And the answer is, I used to say, well, it's more cycles, but now I realize that the number of echoes is the same because the frequency of the rod string is the same, and it doesn't mean anything at all. You're going to have the same number of cycles. All that the real problem is as you pump faster, you have a higher peak load and lower minimum load, and you have a lower ratio of min load divided by peak load. And if it's less than 0.1 for 2,500 feet, you're more likely to have a higher failure rate. So that's what this is about. What's the next well? I talked about gunking the pump. Okay, holding the pump barrel. And we probably had, about every 6 months or so we'll get an example from someone somewhere in the world that says, what's wrong with my well? What is this? And 2 weeks ago, Gustavo and I were talking about one that was a hole in the pump barrel that was local, and I was hoping Gustavo would go out and collect the data, because this sudden release in load is so fast. I would like to know how fast it really is. And so in this case, when we look at this data, we're sampling at about 30 samples a second. And if you sample like 480 samples a second, I think this line would be almost vertical. because it's a really sudden, quick release of the fluid load across the pump. Now, since the rods are stretched, this over travel, when you release this fluid load, the plunger takes off, and sometimes you'll see a little load right here when the plunger is hitting the top of the barrel, or it's like stacking out on the top, and that will tend to get the anchor unset. So a lot of times when you see a hole in the pump barrel, you also see an unanchored pump. So it's very common. See, this well has an anchor in it, and the pump card should look like this, but it's unanchored because of the likely because of the pump would start hitting at the top and unseat the anchor. Now, if we go look at the analysis plot, and we plot the pump load here, and again, you can see that spike load right there, which I'm wondering isn't it hitting at the top. But what I was wanting to show you is that if you come right here and you look at that point right there where the load drops off is 7.13 seconds, and then down at the bottom, that time is about 0.2 of a second. So it's not very much time. I mean, I know how long 0.2 of a second is, and so it's sudden. These kind of sudden load changes are so fast and so sudden. You got to sample fast to see them. And in fact, even at 30 samples a second, we may not be sampling fast enough. It may even be quicker. It may even change quicker than that. So that would be something that would be interesting. Now, once let's look here. This is plunger position. Once it releases a fluid load on the upstroke, notice it over travels, and then there is that, and then there's this thing right there. Is that an echo? Is that what that is? Is that an echo of that release and load, or is that actually some kind of tag? Well, if we plot it versus position, we say, oh no, it's not a tag. It's just the pump just stopped there to harmonic, and so this is the plunger stopping on the downstroke due to that sudden release and load, and that's what that line represents right there. And usually that's an increase in fluid load because when we stopped and the plunger, it just went up a little bit. Look right there, it just goes up. See right there? This increase in load is because the plunger just moved up a little bit, and that to me means that when the plunger stops at that point, the trailing valve goes on the seat, plunger moves up a little bit, and that creates increasing fluid load, and then the plunger starts moving back down, and that reopens the trailing valve for the rest of the downstroke. And that's, if your polish rod, if we were to plot the velocity here, plunger velocity, see how the plunger velocity right here is positive. That means the plunger actually going up. And so if we were to look at the polish rod velocity at that point, change that to polish rod velocity right there. See, the polish rod is moving down about 6 inches per second, and the plunger starts going up about 10 inches per second. I mean, I know there's distance between the surface and the pump, but you would think that would cause a problem with rod-on tubing wear, because the pump actually stops there. Well, you got a problem already because you got a hole in the pump barrel, but your pump actually stops and moves up while the polish rod is moving down at a fairly high speed. So this is an interesting little spike on the data. If we look back at the surface stroke and the pump stroke, let's just go here. The surface stroke is the stroke length of 144 inches. Okay, the pump stroke is maximum plunger travel is 176. So that's 32 inches of over travel for this well. So if your pump barrel, let's say, was 200 inches long, and you weren't spaced near the bottom, and the plunger over travels on the upstroke 32 inches, then you could see how it could get pretty close to the top of the pump and start to tag the pump, and then unseat the tubing anchor. So this is a good example where the over travel is significant, and you have to have a long enough pump barrel where it's not going to tend to whack at the top of this, hit the top of the pump. But this is a good example of over travel when the fluid load is released on the upstroke. Okay. So this is a well that we call an over travel. We call this data an over travel dynamometer card. And the reason why we call this has been classified as the surface card points down and to the right. That's an over travel surface dynamometer card. And that means the pump has a longer downhole stroke than a surface stroke. And so that we call this an over travel surface card and an over travel pump card. Okay, now what Echometer has done when they label a Q-rod over travel on the calculations of the downhole pump card, we're saying that any additional pump stroke that's longer than the surface stroke minus the rod stretch is additional over travel. And that's different than the shape pointing down and to the right is an over travel card. And the downhole stroke is longer than the surface stroke. And how much longer? Well, the surface stroke is about 72.5, and the pump stroke is about 80. So it's almost 8 inches of over travel. See, I said 8 inches of over travel. Okay, well, it's really more than that because your surface stroke minus stretch plus the total inches of over travel. So the stretch is let me figure out what the stretch is. So if we go to annotations and we look at the spring constant. The spring constant for the rod string is 180 inches, 180 pounds per inch. All right, so the fluid load max is 4,132 pounds. So if we're applying for every 180 pounds, we're losing an inch of stroke. You would take 4,132 pounds. Let's just do it here. Come on, calculator, pop up. We'd take 4,132 pounds, and we divide by the spring constant, 180. That means that's 51 inches. So you take the surface stroke, which is 72, minus 72.5. So that's like the surface stroke minus the stretch is a lot. And so the downhole pump stroke, if we were going really slow, would be 72 minus 51. Let's do that. Clear. 72 minus 51. I should be able to get my hand. 21, hopefully. 21 inches. So the pump stroke's only 21 inches without pumping fast. Well, they're pumping really fast, 13 inches, 13.7 strokes per minute. And so they're going from 21 inches of stroke to 80 inches of stroke, almost 81. So there's almost 60 inches of over travel in this pump card, not just this distance here. So the over travel is the surface stroke in inches, surface stroke in inches minus the static stretch, and then that distance from how long the pump stroke is subtracted from the total pump stroke is additional over travel from the pump card. So this pump card has almost 60 inches. I'm calculating it, unless I did something wrong. 60 inches over travel. Wow. I don't remember that slide saying that. All right, so this is an example of the over travel pump card, and it's over traveling because we're pumping too fast. Yeah, this is probably going to have high failure rates because we're pumping too fast. So if we go back and pick the well that has the under travel one. Okay, this one is that it's a deep well, low pump intake pressure, and we have a short stroke. Now, not only do we have a fluid level that's down near the pump, we have some additional mechanical friction, and that's going to also tend to reduce the downhole stroke. So this downhole stroke is 18.6 inches of stroke, and it's pretty close to the right place. I mean, I'd probably put it right about there. Yeah, 18.5, 18.6 inches. And so the surface stroke is 45.4, and the pump stroke is 18. And there's also, you're losing this much of the stretch from to right there. You're losing that much of the surface stroke to tubing movement, which is about 6 inches of loss due to the tubing movement. So we're losing surface stroke due to tubing movement and unanchored tubing, and due to rod stretch picking up the fluid load, and maybe a little bit of stretch due to mechanical friction, and plus we're getting back some due to pumping faster than 0 strokes per minute. So this is and the surface card. How's it plot? Well, the surface card, if we go back to annotations and plot the rod stretch and tubing on the surface dynamometer card, you'll see that this line right here is up and to the right, and that's the slope of a excuse me, a severe under travel dynamometer card. This is a good example of a full pump with under travel. Now, this one that says tagging sampling speed is an interesting one because, well, there's two sets of interesting data. I think we have time probably to talk about both of these at least. So the pump off tag is the well that Ken and I went to out in New Mexico. We went to this well out in New Mexico, and there's 4 sets of data here I want to talk about. If I go to the first data here, this is acquired with a PRT, and this has a downhole stroke of about 130 inches, and the pump is full liquid. And if we look at the strokes, we see that the strokes are the first, I don't know, 12 strokes are full, and then we start to have incomplete pump fillage, and right there we're starting to tag. Okay, but you can't really see it. Why? Because we're sampling at 30 samples a second. So the next one, we said, hey, we need to increase the speed, the sampling speed. And so this well, we were collecting data with TWM and with TIM simultaneously. And this data was collected with the TWM software. And let's see if I can say that. Yeah, TWM import. And so we were collecting this with TWM. And when we looked at the data inside of TWM, all we just saw was these jagged lines because for this well, this speed, the rod string, the wave equation became unstable. But that tag, you could see it in TAM once we had fixed. I think we'd fixed the wave equation at that point in time, to divide the rod string up into smaller and smaller segments so that the wave equation was stable. And so when you sample at a high speed like this, if you don't divide the rod string up into small segments, then the wave equation becomes unstable because of the way the wave equation is solved. Now, how close, how far away is the pump, bottom of the plunger, from hitting? Well, it's really close. Look, that's about 1 inch. So it looks like it was spaced a little bit high, and then once we start to get this additional over travel, then it looks like it's hitting with about a 1 inch. So why am I saying that? Well, this is a really narrow tag, and I think the narrow tag means it's a very short, sudden whack, a tag. If it had started way over here and was wider, then I would say it tagged earlier, higher on the downstroke. But here it's just barely tagging. If the pump had been spaced a little bit higher, then possibly wouldn't even have seen this tag because it wouldn't have moved deep enough in the barrel to tag. Now, this was an interesting well because when it pumped full, it would not tag. And if you look at this stroke right here, when it's full, let's go back to when it's full. Again, you can't really see the real tag because you're sampling too slow. But if we go to the right here and look at a full stroke, right here, full stroke, this overall stroke is 132 inches long versus the pump off strokes, which are 150 inches long. And so that's like almost 20 inches of difference in the downhole stroke. So where's the plunger moving in the barrel? Well, it's moving, not only is it moving down some, it's also moving higher in the pump barrel. So in some fields that have scale, in some scales are a lot tougher, like a barium sulfate scale. If they have scale inside the pump barrel where the plunger doesn't travel, if you were to have a pump off stroke and get this kind of behavior here, then it could stick on the way up, or it could stick and tag on the way down due to scale where the plunger normally doesn't sweep. So this is an interesting example, and it also shows this spike and a spike and a spike. And if we look at this data in terms of time on the analysis plot, we'll see that, let's plot pump load here. Pump load. Yeah, there's a spike, and you can't really see it anymore, but there's probably a spike right there, and then you're kind of losing it. But the time between those spikes is the same time, but different amount of distance. The plunger travels at different velocities, but the time, the property of the rod string isn't changing, and the frequency of the rod string is constant. All right. Now, if I wanted to overlay those two and compare them, then I would go to the field view. Well, I've already done it here. In the field view, I have selected. How do I do that? I go to annotations, and I click on previous stroke. And so in previous stroke, I selected the data from the previous data set at 102.21 with the current data set, and it's showing those two strokes. And so if I go look at this tab right here, this is a stroke that is being overlaid on this data here. If I come over here and I change this to a different stroke, let's change it to stroke number 14. A little bit farther. There. That's a little tag. So now we got stroke 16, and we go over here, and it should show stroke number 16 on. Yeah, it does. All right. So see, even here, the tag is hidden in the sampling speed. You just need to sample a little bit faster. All right, we got a couple more to look at. So this is just a rod part, and we've seen it before. But the main thing I want to show here is that the pump stroke without a plunger, there's no stretch, and the surface stroke is slightly shorter. See here, the surface stroke's 168, and the downhole stroke is 169.5. And if there's no plunger, this is a rod part right at the pump. If there's no plunger, there's no stretch. And since there's velocity, because you're pumping faster than zero, then for a parted rod string that's deep, the pump stroke is going to be always longer than the surface stroke due to over travel. Now, if you don't have any stretch, and you go to the analysis plot, and you plot the polish rod velocity, where's it at? Polish rod velocity right there. And you plot the plunger velocity right here, plunger velocity. They're the same. No, pretty close. Why are they the same? Because there's no stretch. The rod stretch causes the pump to stop, and be out of phase with the surface pumping speed. So in this data here, we're seeing that the surface card and the pump surface velocity, polish rod, and the plunger velocity are the same throughout the stroke. And that's because, again, there's no stretch. There's no pump attached to the bottom of the rod string. Okay, let's see what else we got here. Pick a well. All right, so this data here is not real old, but it's kind of old, and this is when we first started talking about sampling at high speed. And when we go look at this data, this data, if I go to the details tab, this well, this is a good example of a fiberglass rod string. When you see a fiberglass rod string that's tagging, and you see a drop in the surface loads like that, then that means it's a tag downhole, even if you can't see the tag because it's too noisy. And so this is one ugly pump card. It won't win a beauty contest. What do I mean by that? I mean that look at all those bumps. Well, you can't really see what's going on. It looks like noise. And so that's when we started thinking about, do we need to sample faster to see what's going on with the well? These sudden impact loads are so fast we're not seeing them. And so this is 60, and this one's 120. Now see, it's starting to improve, but we can't see that, and we can't see that, and we can't see that, and we can't see that because we're still not sampling fast enough. So we go from 120 to 125. Well, still you can't hardly see it. We go to 240. Come on, is it 240? And now look, you see the tag. You can see the repeat. And if you sample too slow, you need high resolution data and high sampling speed to be able to see stuff like this. It's hidden in the noise if you don't sample fast enough. It smooths out the signal and makes it confusing. Now all we did is go to a little bit faster, 250. No, this is not 250. This is just a valve test. All right. So that's this data, but this is a good example of a. Now let's talk about this again right here. We'll talk about it one more time. So let's go look at the analysis plots, and we'll plot up. And so right there is that what is that? What's that? And so here is the plot of pump load versus plunger velocity on the bottom. And if we pull our, let's change this from pump load for right now. Let's change it into polish rod velocity. Okay, so now I've got polish rod velocity in red and plunger velocity in green. And so if I move to the right here, as I move to the right, and I get to the top of the stroke, right there is top of the stroke. Now, that's where the velocity are close to zero, pump and the polish rod. And now we start on the downstroke, and notice that right here the plunger's actually moving faster right there. The plunger, the pump, is moving faster than the polish rod. And so right here, you've got this long rod that's got fiberglass in it with a heavy weight on the bottom called the fluid load, and it's moving down this fast at the surface, but it's even moving faster due to the over travel and the weight at the bottom of the rod string. I guess that's called inertia or energy. Anyway, it's velocity squared. And then right here, it's slowing down due to compression of the gas. Okay, and then right there, trailing valve opens, and then right here, there's a bounce, and that's see the plunger. So if you look over here, you can actually see it move up and down. See, look, it moves up right there, and it moves back down. See how that that's what the plunger did right there. It kind of bounced due to this compression on the fiberglass rod string, and that's what that is right there. And that's an increase in load due to the trailing valve. It doesn't show it over here, closing and pick up some fluid load, and then as it starts to move back down, open it back up on the rest of the downstroke. All right, I guess that's about, is that about 4 o'clock? It's about time?
Yeah, we're right at about 4 o'clock.
All right. I think that's, is there any more questions we have, Gustavo?
Oh, there's no more questions.
Okay.
Lynn, thank you.
All right. Well, I guess that's it.
All right. Well, thank you so much, Lynn, and thank you, Gustavo, for your help with the questions. And thank you all for joining us. Thank you for your questions and your comments. We hope you learned something new today. And in the event you have any follow-up questions, we always welcome your calls and emails. So please do reach out to us. We do have a schedule posted on our Ask Echometer webpage. If you want to know the exact dates for the rest of the year, then please head on over and check those out. So we appreciate your time today. We're so glad you joined us, and we look forward to seeing you all again soon. Thank you so much, and have a great day.